The Friedenwald Award was established in 1957 as a memorial to Dr. Jonas S. Friedenwald, a distinguished researcher whose contributions encompass the entire field of ophthalmic investigations. This award is presented to an individual in recognition of outstanding research in the basic or clinical sciences as applied to ophthalmology. The 2013 Friedenwald Award is presented to Dr. David Huang at the KCI Institute for his research in the development of OCT technology, which has revolutionized the field of ophthalmic imaging. Dr. Huang was the first to recognize that cross-sectional images could be generated and displayed in false color by scanning the laser measurement beam, thus inventing OCT. Since then, OCT has emerged as a standard diagnostic in clinical ophthalmology and is used for the diagnosis and monitoring of diseases such as glaucoma, corneal disease, diabetic retinopathy, and age-related macular degeneration. Dr. Huang, please come forward. Congratulations. I'm going to ask you to maybe have a seat. I'm pleased to introduce Dr. Joseph Izzat from Duke University, who will review Dr. Huang's achievements and introduce his lecture. Dr. Izzat.
Good evening. I'm truly honored to introduce my friend and colleague, Dr. David Huang, winner of the 2013 Arvo Friedenwald Award. David is currently the Weeks Professor of Ophthalmic Research and Professor of Ophthalmology and Biomedical Imaging at Biomedical Engineering at Oregon Health and Science University. David received his bachelor's and master's degrees in electrical engineering from MIT in 1985 and 1989, respectively. He earned a PhD in medical engineering and medical physics at MIT and an MD from Harvard University, both in 1993. He undertook ophthalmology residency training at the Doheny Eye Institute at USC and fellowship training in cornea, external disease, and refractive surgery at Emory University School of Medicine. David served on the faculty of the Cole Eye Institute of the Cleveland Clinic from 1998 to 2004 and of the Doheny Eye Institute of the University of Southern California from 2004 as Manger Chair in Corneal Laser Surgery until moving to his present position in 2010. David has a distinguished track record of innovations in applying laser and optical technologies to eye diseases. These include his prominent role in the invention of optical coherence tomography. David's seminal article on OCT, published in Science in 1991, has been cited more than 7,000 times. This work, along with the work of the very active OCT research community around the world, has ultimately given rise to a revolution in ophthalmic imaging, as well as a new medical device industry related to OCT components, systems, and OCT image processing and interpretation. In addition to his publications, David has over 30 issued or pending patents in the areas of OCT, mobile health testing, tissue engineering, and corneal laser surgery. He's been the principal investigator of multiple NIH grants, including his current service as PI of 2 major NIH-funded clinical studies, the Advanced Imaging for Glaucoma Multicenter Clinical Study, and the NIH Guiding the Treatment of Anterior Eye Disease with OCT study. I'd like to say a little bit more about David's role in the invention of OCT, as well as its stunning clinical, commercial, and public health impact to date. Here is David with his mother at his first MIT graduation in 1985, and his mother joins us here tonight. And then a few years later, showing off his first OCT system to his father in 1990. David's work on OCT occurred when he was a graduate student in the laboratory of Professor James Fujimoto at MIT, and drew upon that laboratory's leading expertise in ultrafast laser technology. David's work on OCT grew directly from the idea he envisioned as a graduate student that it should be possible to use the coherence properties of light to form three-dimensionally resolved images in biological tissues with resolution approaching that of the wavelength of light, similarly to how the temporal qualities of ultrasound pulses are used to generate ultrasound imaging. This is the first ever OCT image of a human retina, which David published in the aforementioned Science paper. I joined the Fujimoto lab as a postdoc in the summer of 1991, and I remember that my very first day of work, when I first saw David first thing in the morning, he was sitting at a desk actually editing a custom color palette for this image in that paper in Science. Those clinicians among the audience will recognize this color palette, this blue, green, red color palette that was adopted by Humphrey Zeiss for the OCT series of instrumentation and became the early standard for OCT images. Thus, David contributed not only to the technical, but also the artistic origins of OCT. Stimulated by this early work, as well as that by many other contemporaneous groups that were working on related technologies throughout the world, the variety and intensity of the subsequent interest in OCT has been dramatic. As this audience knows well, following about a decade of intense technological development by many groups, including those in the my colleagues in the the technological development community depicted in red here, as well as our colleagues following the pioneering work of Carmen Pulifuto and his colleagues at the New England Eye Center on clinical development of OCT for clinical applications. OCT has now become the standard of care in diagnostic ophthalmology, providing high-resolution images of the retina, optic nerve, and anterior eye that are impossible to obtain by any other non-invasive method. As you know, OCT has played a major role in the development of pharmacotherapy of retinal diseases, such as macular degeneration and diabetic retinopathy. What this audience may not be so familiar with is that OCT imaging is also of intense interest in many other medical specialties. For example, as depicted in blue here, hundreds of papers per year are published in the interventional cardiology literature, where OCT imaging of stent placement and re-endothelialization has stimulated research studies and commercial development, much as it has in ophthalmology. The clinical, commercial, and public health impact of OCT has also been dramatic, as illustrated in these data from Medicare reimbursement studies, which David helped to assemble with Eric Swanson, who you met last night and who you'll hear more about in David's talk, which was published in OCT News. As can be seen here, the number of reimbursed OCT procedures overcame those, that is, retinal scanning procedures, including OCT and some other technologies, but mostly OCT by this time, surpassed those of the other principal ophthalmic diagnostics many years ago. OCT is now the most commonly performed ophthalmic diagnostic procedure in ophthalmology, with an estimated 10 million imaging procedures done per year in the U.S., and a total cumulative OCT reimbursement domestically estimated to almost exceed $5 billion. The OCT equipment market depicted here is also very healthy, with annual system sales in the hundreds of millions. To bring these statistics, which you heard some of last night, down to earth, however, one of my favorite ways of understanding this data is this, depicted here. In a single year, that is 2010, in which they compiled this data, almost a quarter of all Medicare beneficiaries over 65 years old had OCT on at least one eye, and OCT was used between 3 and 12% of all ophthalmology clinic visits in the U.S. And so those of you that have families, it's very likely that this technology David co-invented over 20 years ago has touched a member of your family. As impressive as the invention and continued development of OCT is, it's just one example of David's many accomplishments in research, clinical care, and mentorship of successful trainees and students. Here is David, joined by his wife Hillary and daughter Rianne. Please join me in congratulating David Huang as the 2013 Friedenwald Award recipient.
Thank you, Joe, for that very kind introduction. I was hoping to escape the blame for that color scale. Many people have recognized that with a much higher definition in images these days, that grayscale is actually better at seeing fine retinal details. But I would still submit that back then, the false color was what grabbed a lot of doctors' eyes and was very helpful in marketing OCT and making it a clinical success. So I want to recognize my mother and sister who are here in the audience, and this is an opportunity for me to explain this mysterious technology at length that I have been working on over 20 years. I'm sure they're wondering why it takes so long to keep developing technology, but I'll try to explain why it's so interesting and useful to so many ophthalmologists. And I also want to thank the key supporters who were very important in my career, and they include Dr. Dave Wilson, the director of KC Eye Institute, who provided an ideal environment for our laboratory, the Center for Ophthalmic Optics and Lasers, or COOL Lab. And also the leaders of Doheny Eye Institute, Dr. Ron Smith and Dr. Steve Ryan. Dr. Ryan just passed away very recently, and of course I'd like to honor his memory here as well. And I also want to recognize the co-inventors of optical coherence tomography, who were just at the Champollion Mott Award lecture and reception yesterday. I'm going to talk about some of the same thing that Professor Jim Fujimoto talked about, but with a little bit different emphasis, more on functional OCT. And also, his history of OCT started in the 1960s. My history starts in the 1980s, because I don't remember much of the 60s. So I do have financial interest in OCT technology, especially related to two companies, OptoView and Zeiss. So I'm going to talk about structural OCT. And of course, by now, that literature is very vast, and there's no way for me to encapsulate it. So I mostly talk about the history of structural OCT development and some select applications. I will spend more time talking about functional OCT, in particular two variety of functional OCT that I think will have large clinical impact as they develop in the future. So starting with the history of OCT, as I remember it, it started with a collaboration between Professor Jim Fujimoto at the MIT Ultrafast Optics Group and Dr. Carmen Puliafito then at Harvard Medical School, Massachusetts Eye and Ear Infirmary. So Jim was an expert in femtosecond lasers, and I think Carmen had the idea that it could be useful in measuring distances in the eye using cross correlation of femtosecond laser pulses in a nonlinear crystal, measuring the distance between cornea and aqueous. And this was published in 1986. Of course, this is probably a rather trivial application of a very expensive femtosecond laser, but nevertheless, I think this line of research led to very fruitful clinical applications eventually. So when I look at technologies, I have a bias for looking for innovation rather than looking at practicality at the very beginning. Now, the very first project that Jim gave me actually has nothing to do with ranging or imaging. My first mission was to develop a femtosecond laser for doing intraocular surgery that Carmen was very interested in. So I was working on a regenerative amplifier. Unfortunately, I was not able to get it to generate sufficient power to cut tissue. That all I accomplished was actually being shocked by the 10 kilovolt power source, and also having a hole burn in my jeans by a high power laser. So I think Jim either took pity on me, or maybe he didn't really want all that liability. So he gave me a safer side project, and that is to resume this intraocular distance measurement using a more practical technology. And he showed me this paper by Robert Youngquist that described using interferometry using low coherence light to measure distances in optical components. And so we thought that this is a way to achieve actually higher detection sensitivity, much more compact and cheaper light source, and could be used to do something similar to what had been done using femtosecond lasers, which was, again, to measure the distance between the cornea and the aqueous and the lens through the aqueous, and also detect the reflection from the iris. Now, of course, instead of using femtosecond lasers, we use a semiconductor light source and an interferometer to capture axial depth information. And so the resolution of OCT relates to the coherence length or bandwidth of the light. And that is its very special feature. And from that first experiment, it was simple to extrapolate it to an imaging technology that we call optical coherence tomography, where we take that OCDR or reflectometry scan and translate it over the transverse direction by scanning the light beam and compiling an image that we could then display either in grayscale or a false color scale. So that was probably my biggest contribution to OCT. Of course, it's very simple in concept, but it did drive the direction of research. It opened up a lot of new clinical applications, and in terms of technology, it made higher speed paramount. So achieving higher detection sensitivity and speed was greatly facilitated by Jim's introduction of me to Eric Swanson. Eric was the leader of the optical communications group at MIT Lincoln Laboratory at that time. Of course, he has very deep knowledge of this area and vast resources at Lincoln Lab to fabricate state-of-the-art components and systems. So our project progressed very quickly to one where we could collect enough data to publish the first OCT paper. Now, we were looking for tissues with fine layer structures or very detailed features that could be optically accessible. And we identified the retina, of course, which has this nice, bright nerve fiber layer that you could recognize, along with the retinal pigment epithelium. We also imaged coronary artery plaques and gastrointestinal tissue, actually. So I ran around the Harvard Medical School system, begging people for tissue, and scan those tissue. And the retina and the coronary artery plaque turned out to give the best images, and that's what we published. Our eye work, of course, was done in collaboration with Dr. Carmen Puliafito, and Dr. Joel Schumann was the one who actually did the experiments with me. He took over calf eyes and human eyes and cut them open, and he actually taught me retinal anatomy and optic nerve anatomy, and that's probably part of the reason that I came into the field of ophthalmology. It's because of the knowledge that he taught me. And Jim had this concept then that this is a new imaging modality where the resolution is high enough that it could eventually replace histology. So we are doing non-invasive histology. Of course, the resolution then wasn't nearly as good as histology, but it is getting close now with a steady improvement in resolution and definition. So OCT is based on interferometry performed over a wide spectrum. I think that would cover both time and Fourier domain OCT. And again, the axial resolution comes from a short coherence length or a wide spectral bandwidth in the light source, either instantaneously or scanned over a short cycle. Now, we probably all know that using confocal microscopy, you can also have fairly good axial resolution. And OCT, the way it's set up with fiber optics, is akin to a confocal microscope. So what is the special thing about OCT? Well, it can achieve, the difference is that uses coherence gating to achieve very high axial resolution, so that you don't really need very high numerical aperture or tight focusing to achieve good axial resolution. So in confocal gating microscopy, you have a confocal gate that is the confocal parameter of your light beam. Of course, that depends on how big the input beam is, what the numerical aperture is. And in OCT, you do not have to depend only on that, but your axial resolution is also helped by having a wide spectrum or short coherence length. And usually in OCT, this coherence length is much shorter than the confocal parameter, giving you much better axial resolution. And even in OCM, or optical coherence microscopy, this coherence gating is also usually stronger. In addition, this coherence gating help filter out multiply scattered light and usually give you a deeper penetration into turbid tissue. So OCT axial resolution is a convolution of the coherence gating waveform and confocal gating, and usually coherence gating is much stronger. OCT was made possible by the advances in optical technology. The two primary examples are the semiconductor light source, namely LED or superluminescent diode, and optical fibers. Now, these were developed due to the burgeoning optical communications industry at that time, and not for OCT specifically. But now OCT is actually a major customer for these technologies. Now, these technologies just happened to become available when I was working in Jim's laboratory, so I was very lucky. And I think several groups of people recognize these technological developments, and several precursors for OCT were described in the literature since 1987. Of course, the Youngkis paper. It may not be the most important paper in the field, but I recognize it because that's the first one that I read. And there were also Dr. Furcher's group in Vienna who were using it to this kind of technology to measure eye length, and that actually led to another very important biometry technology and product in ophthalmology. And Dr. Tano in Japan actually patented this coherence ranging technology for biomedical applications as well. And of course, we did when we performed the first ranging measurements in the anterior chamber. Going from ranging or reflectometry to OCT, I think several groups also recognize the potential for this as an imaging modality, and that include the MIT group, and first described in our science paper, but also, again, Professor Tano in Japan at Yamagata University has patented an OCT technology, as well as Professor Furcher's group in Vienna. So part of the reason for the success of OCT was picking the correct initial clinical applications to investigate, and these include retinal imaging. So this is our first retinal image in 1991. And this is 2012, and very high resolution, high definition 3D imaging is now possible. And there are about 20 million patients a year who undergo this type of imaging clinically. And in coronary artery imaging, there are now several companies with product for coronary artery angioscopy based on OCT. And in 2012, there were approximately 100,000 patients being scanned, and that number is increasing rapidly and exponentially because it's a relatively new clinical technology. And these are based on numbers compiled by Eric Swanson in OCT News. And of course, this is also driven by the improvement in technology and about 1,000-fold improvement in speed over those years. Now, I want to also briefly talk about several key choices that were made for the successful implementation of early time domain OCT technology that now are taken as a matter of course, and these include the use of fiber optics, external reference reflection, and heterodyne detection. So the first OCT system that I built was a copy of the Youngkis paper, and it's built in free space. And what, of course, I was aiming for was that the sample reflection and the reference reflection are perfectly matched in transverse spatial mode, so that you have high contrast interference fringes as this reference mirror is scanned back and forth in delay. But in reality, I could never do that. Usually, if on the detector plane, the modes look like that. So there's reduced fringe contrast or reduced signal-to-noise ratio. And I think an important step forward was to couple the light in a single mode optical fiber, so that the mode, by definition, in a single mode fiber, are perfectly matched. And this solved the mode matching problem, improved signal-to-noise ratio, and of course made the construction modular, so that the manufacturing and alignment of the system become much more tenable. And the design we use then, and which is rather standard, is to use a Michelson interferometer, where the reference mirror is outside of the eye. And this seemed a matter of course now, but actually there were alternate designs. For example, the first demonstration by Professor Furcher's group used a Fabry-Perot interferometer, where there are a dual beam, if you consider one beam reflected from the retina that's interfere with a beam reflected from the cornea. Now that, of course, restrict the field of view fairly severely, and also reduce the sensitivity. So that was not a viable design for OCT, although, of course, that technology became a very commonly used biometer. I want to talk about the 501 OCT patent that Eric Swanson was mainly responsible for, filed in 1991 and issued in 1994, that what became the template for commercial OCT development. Eric was at MIT Lincoln Laboratory at the time when he worked with us. And he later on became the chief technology officer for Sycamore Network, and also was a co-founder of Light Lab Imaging. So, and these are just two main examples of the many companies that he were involved with. So he was very important in the technology startup field, including OCT, and he's very deservedly a very rich man from all these activities. The first OCT systems for clinical studies were developed under the supervision of Professor Jim Fujimoto. And, of course, Eric at Lincoln Lab was essential for this effort. And after the initial work in vitro demonstration, shortly after that, I had to leave for my clinical rotations at Harvard Medical School, because I was an MD PhD student. So most of the initial clinical studies were really done with scanners that were developed, and software that were developed by Michael He and Joe Izot. Michael was also an MD PhD student that took over my project, and he turned out to be a better engineer and a fine writer, and was responsible for much of the early literature, the early algorithms for acquisition and signal processing and image processing. And his PhD thesis was really actually my OCT Bible for a number of years. And Joe I have to say his analysis of OCT is probably the most correct and clear. So his OCT chapters are now my OCT Bible. And if I have a student who asks me about OCT, I just point them to Joe's book chapters, which are much better than my usual hand-waving explanations. And Joe was the first to construct a corneal OCT system and wrote the first article on the clinical corneal and anterior segment imaging. And later on at Case Western Reserve University, he also developed a very high-speed time domain OCT system that became the basis of an anterior segment OCT system that we actually collaborated on when we were both in Cleveland. The first clinical retinal OCT imaging were done in Dr. Carmen Puliafito's clinic. I think by then he was at Tufts, and Michael He had played an important role in that. He was the first author of this first paper that described OCT used clinically to image the human retina. And Joel Schumann was, of course, responsible for introducing OCT into the glaucoma world by scanning the nerve fiber layer around the optic disc and measuring it quantitatively, and at this time is still the primary means by which OCT used to detect damage caused by glaucoma, and this was published in 1995. Now, everybody knows that in 2006, there was a big generational leap in OCT technology. Before that, Zeiss made several time domain OCT systems with a speed of 100 and then 400 axial scans per second. And in 2006, this was increased to 26,000 scans per second with the first product that was introduced. It's like developing a jet engine for the first time compared to an old propeller. And so commercially, at least, the Fourier domain technology was about 100 times faster. And I want to recognize someone who was very important in the development of commercial OCT technology in the eye, both using time domain and Fourier domain OCT technology. Here's Jay in 1994 at Humphrey, which was later acquired by Zeiss. And he was then the program manager for OCT. And his prototype then ran at 40 hertz per axial scan repetition rate. And then the later system that he introduced include OCT 1 and 2, which performed at 100 hertz axial scan repetition rate. And the Stratus in 2002 at 400 hertz. And then he also worked on a prototype of Visante before he left Zeiss in 2003. And that ran at 2,000 hertz using the technology that Joe Izat developed. And then he formed his own company called OptoView and introduced the earliest Fourier domain OCT technology in 2006 at 26,000 hertz. And now there is a model that runs at 70,000 hertz. So in one person, he experienced the Moore's law of commercial OCT. And if you plot all these systems that he was involved with, and usually he was involved with the very early development, the speed actually doubles every 1.6 years, and that really bears a remarkable resemblance to the Moore's law in semiconductor and computer industry, where either the density of integrated circuits or computing speed or memory capacity would double every 1 or 2 years. Now, you might think, well, it can't really get any faster than this. But, Moore's law in the computer industry have been going on for 50 years. So many predictors of the demise of Moore's law in those areas have been proven wrong. And so I think by 2019, we'll have megahertz commercial OCT. And if you think that's unrealistic, actually it has already been demonstrated in the laboratory in Robert Huber's group. And that was in 2010, multi-megahertz OCT imaging. So for those of you who are not old enough to remember time domain OCT, I'll briefly explain how it works. So in time domain OCT, you have a low coherence light source, a superluminescent diode that launches light that's split into the reference and sample arm, the sample arm being a scanner for the eye. And the reference arm actually have to move back and forth every time you want to get an axial scan. And the signal is conditioned and then acquired by a computer. And so to build an image, this mirror have to go back and forth several hundred times, 1,000 times, and that limits speed. You see, it takes a long time. And Fourier domain OCT it operates a somewhat different principle. Joe will call this revisionism, because these nomenclatures develop and kind of evolved, and now I'm going back and changing them a little bit. But I like to think of both spectral or spectrometer-based OCT and swept source OCT as both variants of Fourier domain, one using a superluminescent diode and a spectrometer, and the other one using a tunable laser and a sequential detector. And both depending on a Fourier transform usually performed in a digital computer to reconstruct the image. So in a Fourier domain OCT of the spectral variety, the reference is stationary. And when you want an axial scan, you go look at the spectrum captured by the line scan camera, and each spectrum yields an axial scan. And the line camera rate can be very fast, many thousands or even hundreds of thousands times per second. Not only is FDOCT faster because of the lack of reference arm mirror motion, but it's possible to run it so fast because it's more efficient in terms of capturing signal. So the signal-to-noise ratio of OCT has a lot to do with the integration time at the detector. And for Fourier domain OCT, that integration time is the time to acquire a spectrum, and that gives you a whole axial scan. Whereas in time domain OCT, it's akin to the time it needs to acquire a pixel or a resolution element. So the signal-to-noise ratio advantage of Fourier domain OCT over time domain is roughly n over 2, where n is the number of spectral elements. And that could be very high, hundreds or usually thousands. And that's why Fourier domain OCT is so much better. Fourier domain OCT actually has, in terms of the precursor concept being around for a long time, again, Professor Furher's group has looked at spectral modulation in interferometric eye length measurement again, and piston measurement. And this has also, this literature also appeared in Japan with Dr. Kubota. I'm just quoting these two articles because I'm familiar with them. I'm sure since then, around that time, there are actually many Fourier domain or spectral domain reflectometry papers due to the optical communications industry rapidly developing then. But we actually reinvented the wheel a little bit. Fourier domain OCT was actually in my PhD thesis that was completed in 1993 at MIT. And also, Eric Swanson had put it in our 501 patent in 1991. And we were actually not aware of the Fourier domain reflectometry literature. And the way we discovered it was kind of reinventing the wheel, where the first time we were building a fiber optic OCT system, we found the resolution was terrible. And we were investigating it with a spectrum analyzer and found all these interferometric fringes. And Eric was very sharp. He immediately noticed that these, the fringe spacing was related to the mismatch between the reference and sample delay. So that's when we started to think about looking at the spectrum to perform OCT. So that was in November 1990 when he noticed the relationship there. And I have a philosophy where I always think of something to make lemonade out of lemon. So this is, and that occurred many times, and this is one of those lemon movements where I think, well, okay, our fiber optic OCT works very poorly, but this gives us some information where we can think of an alternative way to perform OCT. So I wrote up this note for a coherence domain reflectometer with spectrometric detection also in November of 1990. I actually thought of it only as a way to make the OCT faster because the mirror doesn't have to move. But Eric actually recognized the signal-to-noise advantages because he was familiar with the LiDAR technology, specifically chirp LiDARs, which were developed at Lincoln Laboratory. He was familiar with that because he was a leader of the optical communications group at Lincoln Laboratory. And the papers from Lincoln Laboratory clearly show the sensitivity and speed and the implementation advantages of doing things in the spectral domain. And so that's how he came to put Swepsworth's Fourier domain OCT in the 501 patent as shown in this figure. And another group also published in SPIE in 1998, again showing actually a dynamic range or signal-to-noise analysis. There were, in the intervening time, before FDOCT was widely used, there were many early demonstrations, again by Professor Furher's group, looking at measurement of intraocular distances. Eric Swanson and Chin did OCT using a frequency tunable laser. And also groups in Poland and Austria were working on this type of OCT technology. And the Medical University of Vienna, the group include Professor Adolf Furher and Christoph Hitzenberger and Rainer Leitgeb, and the MIT group, of course. And the group at Nicholas Copernicus University in Poland include Maciej Wojtkowski and Dr. Andrzej, I think Kowalczyk. Excuse me if I'm mangling these pronunciations. But But it wasn't until 2003 that the signal-to-noise ratio and speed advantage of Fourier domain OCT was widely and clearly known. And these were due to the work of several groups publishing in the same year, including Joe Izod at Duke University. His publication, I think, was the first time where the sensitivity advantage of both swept source and spectral types of systems were analyzed and shown to be equivalent and being much better than time domain OCT. And similar analysis or demonstration were also made at the Harvard Medical School, Massachusetts General Hospital, Wellman Center for Photomedicine Group, including Johannes de Boer, Brad Bouma, and Gary Tierney. So what made Fourier domain OCT possible? It's really the advances in the key optical components. I think if I were to work on Fourier domain OCT in 1991, I would not be able to demonstrate the signal-to-noise advantage because the components are too slow. So you need fast, very high-speed line camera, which were originally developed for machine vision, or rapidly tunable laser, which were developed for optical communications, or at least the high-performance versions were developed during the 1990s to a state where we can use it to perform high-performance swept source OCT. Well, the availability of Fourier domain OCT really led to an explosion of new products, and here are 8 companies and 8 machines, but there are actually more than that now that you can see on the exhibit floor. So what drove this industry, or what sustained it, was really the development of anti-VEGF therapy for neovascular age-related macular degeneration. So these patients require nearly monthly injections, and often OCT is used to make the initial assessment, and also determine whether a patient needs an injection or not on a roughly monthly basis. And here's a high-definition Fourier domain OCT that shows this edema, which is probably leakage from a choroidal neovascular membrane. So OCT was also fortuitous that other researchers who may be present here who developed anti-VEGF therapy for this disease. And of course now high-quality OCT imaging is widely available in many commercial products, leading to the ability to see very thin layers, including looking at the photoreceptor outer segment length that is prognostic of visual vision. And of course, adding adaptive optics and ultra-high resolution OCT can give you extremely high resolutions in all 3 dimensions. And there are many excellent work. I'm just picking one out because this is familiar to me, where this technology was used to look at the cone mosaic, and also in the cross-section resolving parts of the photoreceptor. Very high-speed OCT is now making true 3D OCT imaging possible. This is very dense volumetric imaging over a very wide area. This is 12 by 12 millimeter area performed by Professor Fujimoto's group in collaboration with Martin Krauss and Joachim Horniger at University of Erlangen. And these wide field 3D OCT technology, I think, will lead to great improvement in the management of glaucomas as well. This is an example where this wide field imaging can clearly show a nerve fiber layer defect on this reflectance ratio map. And this also shows up very clearly on the OCT on FOS image of the rim. And this is a nerve fiber layer thickness map, and you can see this clear bundle defect, and you can see the damage to the ganglion cell complex by its thinning. This is ganglion cell complex thickness map. So I think for structural imaging in glaucoma, I think that's the way it's going. It's going to be much more finely sampled, and we'll be able to measure focal defect and correlate them with visual field. And combining this information from several anatomic regions, such as the peripapillary nerve fiber layer, the macular ganglion cell complex, and this topography, when you combine them, you can get a much higher diagnostic sensitivity. The best single parameter in this study from our advanced imaging for glaucoma study was a ganglion cell global loss volume at 72% sensitivity for 95% specificity, and for a combined index was nearly 83%. And OCT can also be used to predict glaucoma visual field progression. Those with strong OCT parameter, predictive parameter, have a higher chance of developing visual field progression. In a study that we performed in our advanced imaging for glaucoma study, we found that the ganglion cell complex focal loss volume was the best parameter. Those with greater than 5% volume loss compared to normals have a 40% chance of progressing after 6 years, compared to 5% for similar glaucoma patients at baseline. OCT is also used for anterior segment imaging for applications such as measuring corneal thickness and corneal power. And the power is very useful in post-LASIK cataract surgery intraocular lens power calculation, where if you just measure the anterior surface using traditional keratometry, you will have erroneous results. It's necessary to take into account both the anterior and posterior surface, which were no longer parallel after LASIK. And this is a 3D corneal OCT that was being used to simulate PTK. Now, this is not used that much because PTK is not a high-volume procedure, but I use this all the time, and I love it because you can see things in 3D before the surgery. And now I want to talk about new developments in functional OCT. And the functional OCT technologies that I want to talk about include measuring the Doppler shift between consecutive A scans and using that to compute total retinal blood flow, which is an indicator of global ocular circulation, and performing angiography by looking at the correlation between consecutive B scans, and that's a measure of local circulation. There are other ways to perform angiography, and there are other types of functional OCT. I emphasize these two particular technologies because we have developed them, and I think they have great clinical potential. It's important to image blood flow because the leading causes of irreversible blindness are all associated with abnormal ocular circulation. And these include glaucoma, diabetic retinopathy, and macular degeneration. And even though there are already many methods of imaging blood flow, we still need a technique for rapid and accurate quantification of ocular blood flow. Fluorescein, as you know, is qualitative, and Doppler ultrasound, due to the low spatial resolution, is not accurate. Laser Doppler can give you accurate results, but the current technology measures one vessel at a time, so it's very consuming to measure global ocular blood flow. And at this juncture, I'd like to acknowledge the Doppler OCT volunteers, which pioneers, which include the group at Beckman Laser Center at University of California at Irvine, Dr. Tom Milner, Yanghua Zhao, Zhongping Chen, and Stuart Nelson. Also, Christopher Peterson at Zeiss had a very early patent in this technology. And again, Joe Izat and his graduate student, then graduate student, Siavash Yastanfar, who I believe were the first to show Doppler imaging of retinal blood flow while they were at Case Western Reserve University. So these were all done with time domain OCT technology, but it was very easily ported to Fourier domain OCT. And my group did not develop any fundamental Doppler OCT technology, but we thought of a clever scan pattern to very quickly measure total retinal blood flow. So we did concentric scans around the optic disc, and with that we obtained on color Doppler display these circular scan sections that show all the branch artery and veins that emerge from the optic disc. We then process these concentric and really parallel sections and look at the cross-section of the blood vessels. And because we know the relative position, axial position, in these two sections, we can compute the Doppler angle, and along with the Doppler shift cross-section, we can then calculate the cross-sectional flow from each of these vessels. And using that technique, we could calculate hemispheric flow or global or total Doppler, total retinal blood flow. And in an early pilot study, we showed that retinal blood flow was decreased in several diseases, including glaucoma, optic neuropathy, and proliferative diabetic retinopathy. And looking at a larger group in glaucoma, we performed correlation study where blood flow was always in the model, and then we also put in the same model some sort of structural parameter such as rim area or nerve fiber layer thickness, global average. And we found that in correlation with visual field mean deviation, blood flow was much more important with R-square correlation coefficient around 0.25, whereas these structural variables were around 0.1. So according to the correlation, blood flow is actually more than twice as important as structural variables in explaining the variation in visual field mean deviation. So this certainly suggests that blood flow could be an indicator for glaucoma and could be very important. There's, in that paper, we found very little correlation between blood flow and structural measures that reflect the thickness of ganglion cells or nerve fibers, and a big direct correlation with visual field. Now, with that double circular scan pattern, it's quite laborious to measure all those Doppler angles semi-automatically. So I think the future with higher speed OCT is actually to compute the Doppler shift on fast sections of blood vessels and integrate the flow that way, because that actually obviates the need to measure Doppler angle and could be automatically processed. The downside is that high speed is needed, probably around 100 kilohertz, but that is becoming available commercially. And I want to acknowledge Professor Jin Fujimoto's group for developing this type of flow computation. And this was published in 2011 by Bernard Baumann. I think there was actually one earlier publication that I didn't put in. And then finally, I want to talk about OCT angiography, a topic that I'm most excited about. And again, I want to acknowledge the pioneers in this area, and they include Dr. Ricky Huang, then at Oregon Health and Science University when he initially did this work, but is now in Seattle and right here in the audience. And he was the earliest, along with Professor Yoshiaki Yasuno at Tsukuba University in Japan. And he was actually just now elected to the program committee of the MOI cross-sectional group. And also Ben Bakash at Harvard MGH Wellman group did very important work in performing OCT angiography of tumor vasculature that was published in Nature Medicine in 2009. Our group started working on this using a high-speed swept source OCT unit developed by Professor Fujimoto's group that ran at 100,000 axial scans per second, ran at 1050 nanometer, which is slightly longer wavelength than standard 840 nanometer retinal OCT. So this penetrated a little bit deeper, and the axial resolution was 5 microns. And this system is similar to the one described by Ben Potsdam in Optics Express in 2010. And the way we perform the angiography scan is that we perform 8 B scans or cross-section at the same location consecutively, and then we vary the position to build up a whole volumetric cube. And so this is a 200 by 200 cube. And this is done in about 3.4 seconds. And by comparing these B scans, we can detect flow by looking at the variation in amplitude at each voxel. So if the voxel is within a blood vessel, the amplitude would go up and down as a blood cell passes through that volume, or it twinkles. If it's static tissue, such as a nerve fiber, then this amplitude of reflection would be static. So we can detect the flow by decorrelation of this amplitude. And we like the decorrelation function because it doesn't depend on the mean reflectance signal amplitude. And this can give you a flow image where flow is bright and static tissue is dark. But if you just use the standard OCT images to compute a decorrelation, what we found is the signal-to-noise ratio was relatively poor. So we came up with an algorithm to get more OCT frames for nothing, basically. We split the spectrum into 4 spectral bands and formed OCT frames in each spectral band and performed decorrelation using these low-resolution OCT frames. And then we have a large number of decorrelation images, and we averaged them, and that improved the signal-to-noise ratio greatly, and I believe that's due to decreasing the sensitivity to motion, decreasing bulk motion noise, and also decreasing speckle noise. And you can demonstrate the signal-to-noise advantage by comparing split spectrum processing to full spectrum processing, where we can see the vessels more clearly with less background noise. And it's even more clear when you look at a en-face maximum flow projection, where the angiogram is much more continuous using the split spectrum or SADA algorithm, and there's much less noise in the foveal avascular zone where there shouldn't be any vessel. And this was work mainly performed by Dr. Yali Jia in our group, and published in 2012 in Optics Express. We also use a 3-dimensional orthogonal registration algorithm to remove any motion artifact, and this algorithm was developed by Martin Krause from University of Erlangen in collaboration with Jim Fujimoto at MIT. So this is a registered angiogram, and you can see the fly-through cross-section where we can see distinct vessels in the retina, in the inner retina, and near confluent choriocapillaries. You can also image the optic disc area, where you see large and small retinal vessels, near confluent, very strong flow in the choroid, and also a lot of flow in the disc, both superficially and deep in the lamina curvosa on the scleral plane. So large retinal vessels, choroidal vessels, superficial disc vessels, and very deep disc vessels on the scleral plane. This being a 3D volume set, you can also slice it in another way from superficial. This superficial disc, this is choroid, and this is lamina curvosa. I find these kind of mesmerizing. So this is deep in the lamina curvosa. You can still see some flow in places where there's no shadowing from overlying vessels. So again, superficial disc. So here are two examples. One is a normal disc, and you can see by the OCT angiogram that there is a fairly dense vascular network throughout the disc. You can see the fine vascular network and also the large retinal vessels, of course. And in the pre-parametric glaucoma case, this vascular network is less dense, and you can quantify it by averaging the decorrelation value over the entire optic disc. And in this case, there's clearly decreased flow. We have a larger pilot study comparing 24 normal eyes in 24 subjects, compared with 11 eyes from 11 glaucoma subjects. 8 of them are pre-parametric or having visual field damage, and 3 did not have visual field damage yet or are pre-parametric. And what we found was that, first of all, OCT angiography flow index was highly repeatable. In the same session, the repeatability is about 1%, and intervisit is about 4%. And best of all, the variation within the normal group is very small, 5%, or actually less than structural measurements such as global OCT nerve fiber layer thickness. So that's very promising for glaucoma diagnosis and for glaucoma tracking. In this group, of course, visual field and structure both show difference between the normal and glaucoma group. And in terms of flow, in the glaucoma group, there was a 25% reduction in the optic disc flow index. And this was, of course, highly significant. It also correlated very well with visual field. The optic disc flow index and the visual field pattern standard deviation have a coefficient R of minus 0.84. And there's basically no overlap between the normal and the glaucoma group. So in this very small study, there's 100% sensitivity and specificity. Of course, a much larger study is needed, but this showed a lot of promise. So concluding this particular pilot study, we found that optic nerve head microcirculation is reduced in glaucoma, and even before visual field damage, this could be detected by quantitative OCT angiography. And the flow index was highly repeatable and very consistent within the normal group, 5% coefficient of variation. It's highly correlated with visual field and may be used for a very useful new tool in glaucoma. The investigation in glaucoma is just starting. We are also performing pilot studies of OCT angiography in age-related macular degeneration. This is an example of type 1 choroidal neovascularization, where you can see the color-coded angiogram that the yellow CNV is between the RPE and the Brooks membrane. So we coded the inner retinal flow blue, outer retinal flow yellow, and choroidal flow red, and overlaid it on a structural OCT image so you can see everything in one picture. And this is, could also be looked at on FOS, and you can measure both the area and the flow index of the CNV. And this CNV had a flow index of 0.127 or comparable to the parafoveal vascular network. Here's another example where it's notable that it's actually a hemorrhage covering the CNV so that it doesn't show up very well at all except for a very tiny dot on the fluorescein angiogram. But you can see this clearly on the OCT, and it's type 1 because it's between the RPE and Brooks membrane. And again, you can measure both the area and the flow index, so it's quantitative. Here's another example where the CNV is above the RPE or type 2. And this is a large CNV with core vessels and kind of lacy fronts that you can see. It's extremely high flow or active, 0.146. And it was associated with a lot of fluid leakage, as demonstrated by the cystic space right above it. And this is a fly-through of this type 2 CNV, showing also underlying choroidal circulation, inner retinal circulation, and cystic structures, showing the activity of the CNV. And again, you can look at it with layer-by-layer fly-through, giving you an even better appreciation of the transverse extent of the CNV. So this is very new, unpublished data, and I think they look very amazing. In many ways, it's superior to fluorescein angiography because it's three-dimensional, and you can separate the location by layer, and you can measure the amount of flow. So the advantage of OCT angiography compared to fluorescein, it's three-dimensional, so you can separate the separate circulations. You can distinguish CNV above or below the RPE, and you can section project along any plane. It's quantitative. There's no injection or side effects. The disadvantage, of course, is that right now we can only scan over a small field of 3 to 4 millimeters, but the field will increase with higher speed. Actually, Professor Fujimoto just showed yesterday a 12 by 12 angiogram using a higher speed OCT system. You cannot visualize staining or leakage, but you can visualize fluid accumulation in cysts in the retina. So I think functional OCT has a very bright future that we're just starting to see. It's just like structural OCT 10 years ago, where very few people are just investigating it. But I predict that in 10 years, people will think that fluorescein and ICG injections are barbaric and totally unnecessary because you can do the same thing non-invasively. So finally, I'd like to acknowledge the support of National Eye Institute for the research grants, RPB and OptoView, and my Advanced Imaging for Glaucoma NIH-supported Grant and Study Consortium, and our collaborators at MIT, University of Erlangen-Nuremberg, and Casey Institute Glaucoma Service and Retina Service, and also members of the COOL Lab. And I will post this lecture online on coollab.net. Thank you very much.